Okay, yeah, so I'm really happy to be here. Please do feel free to ask questions throughout if there's something that's unclear. We should have plenty of time for the conversation, although I did throw in a lot of extra things this morning that I'm excited about. And the main theme of what I want to be talking about today is how can we get robots to contend with manipulating collections of objects which they haven't seen before, and doing that for kind of sequencing of tasks. So not just single pick and place or pushing actions, but really achieving longer horizon tasks. And my work throughout my entire career has really focused on how can we have robots that have the ability to contend and manipulate objects with which they have no prior knowledge. So last night at dinner we were talking about making nice pour-over coffee and how it's hard to get that in Germany these days. And so, but if you were to come to my home, you would see these objects and you would be able to kind of infer what you could do with them even if you hadn't seen them before, right? So things like, I could grasp these objects. There's also, buttons you could press, and there's surfaces you could place things on. And a lot of the work I've done in my career has looked at, inferring these kinds of affordances and then building representations with which we can manipulate using those affordance models. And I'm going to talk a little bit about that. But another thing I'm very interested in, as of recently, is there's a lot of other things that you don't directly observe in this scene that you might want to also reason about. So for example, what are inside these containers, right? You can't see right now. Or what's behind things under occlusion. And also, what's out of the field of view of the robot? Is there anything out there that I maybe need to think about? Like where I can get water to put into the kettle. And so kind of motivated by this high-level idea of being able to infer what we can do, reason about it to kind of achieve some task like making a cup of coffee, I'm going to focus on the following specific questions today. So first is how can we endow robots with kind of an affordance-based reasoning in terms of giving them policies that they can execute for novel objects? Second is, how can we extend this kind of reasoning to reason about more than one object at once in terms of how they might interact if we were to take an action? How can we then reason about what's unseen in these kind of multi-object representations? So looking at ideas of memory for planning. And finally, some very recent work we've done on how can we learn after we've already deployed the robot, specifically learn from when it fails in trying to execute something that it thought it would succeed at. So I'll work through each of these in turn. The first and probably shortest will be this first question of affordance-based reasoning. And this is going to be focused really on kind of multi-fingered grasp learning that we've been working on for a long time. So I could talk a lot more about this, but I'm kind of tired of talking about it. And some of you have seen me talk about it in the past. But I want to give the basics of it because it kind of informs how we go about doing the more complicated work. So these are both old papers now. But if we think about kind of traditionally in robotics, when we think about grasp planning, we might have some sort of model-based representation of our object, like shown here on the left, which you then perform some sort of optimization over some kind of physics-defined metric for what a good grasp is. This was kind of traditionally how we've thought about grasp planning. And while it can give you good grasp, it doesn't really scale well to this idea of novel objects, right? That if I have some object in the environment that I haven't seen before, if I were to use a method like this, I need to first do a complicated reconstruction or lookup problem to try to find something that looks like it. And so instead, the field has moved, we think recently to robot learning, but this work from Ashutosh goes back to 2006 on kind of using sensory-driven perception with learning. Right? So I take some observation of the object as an image or a point cloud, and then I have some learned representation that enables me to predict what a good grasp is. And so we're going to be looking at this second form, and we're going to look at a specific form of it where the primary tool is going to be a grasp classifier. So we take some sensory input, we take a configuration of the hand. In our case, this is something like the pose of the wrist, as well as the joint positions of the two proximal joints on each hand, so the two joints closest to the palm. And then you would move the robot there. It closes using a grasp controller. It lifts the object. And if it succeeds, we can label that as a successful grasp. If it doesn't succeed, we label that as a failure. We now have a very simple supervised learning problem where we can use, your favorite neural network to represent this. The question, though, that's more important than necessarily the representation of the classifier itself is where do you get sufficient data for training a modern, large-scale neural network that requires a lot of data? And so this is one of the first kind of, important lessons for informing how we're going to do things throughout the talk is large-scale training and simulation. So we can use simulation where we have privileged state information to easily get these labels, to also automatically have the robot do exploration for generating this training set, where we don't have to have humans babysitting it. And we can, in fact, parallelize this and get very large-scale generation, while we're out doing other things. Okay, so then given that we can train one of these classifiers, we still have the problem of synthesizing a grasp at deployment. So I see a new object. How do I find what grasp to use? Kind of in the literature, what had been proposed early on were things like sampling. These typically required some sort of heuristic to generate plausible samples that you were then refining with your grasp evaluator, the classifier. But they typically didn't scale to these high degree of freedom, multi-fingered hand scenarios that I'm interested in. An alternative to doing the grasp classification is to do a regression-based approach, where you give the image and you try to predict the grasp. But a naive version of this kind of assumes that there's only one good grasp per object. Right? You're going to be averaging across that, and we know that there are many grasps that work for different objects, and that depending on the context of what task you're trying to achieve, you might want to select one grasp versus the other. And so the classification approach allows us to represent all of those. There are ways we can get multimodal and representations for regression, but in our experience, they're still not good enough alone to immediately be usable in the on the robot. Okay. And then finally, you could also do reinforcement learning. You could directly try to learn a policy for doing all of the grasping. This is generally not data efficient. And then also, one of the downsides is you spend time learning things you already know how to do, right? We know how to do motion generation to move the hand to get close to the object. So I'd prefer not to relearn that, but instead focus on learning the bit I really don't know, which is what does a good grasp look like given a point cloud. So we instead want to view the grasp planning problem as a planning as inference problem. So given this trained classifier where we can treat the output as a probability of success, we'd like to find the grasp configuration theta that maximizes that probability. And we can additionally add model-based constraints onto this optimization. So here I've just shown something like the joint limits of the hand. We can also do that for the arm, so we can make sure the kinematics and reachability of the problem are encoded in this inference problem. Note we also have a prior over the grasp theta, which we model using a probabilistic generative model. So most commonly we'll use something called a mixture density network, where we have a neural network that predicts a Gaussian mixture model over grasp configurations conditioned on the point cloud data. And this serves as a regularization that means we don't try grasps that are far from the data the robot's observed during training. And additionally, we can sample from this to initialize the inference procedure to optimize over the grasp configuration. So kind of using this paradigm, we've done a number of things with multi-fingered grasping. So first, if I look at the means of kind of the prior components, we see we have one that's kind of this grasp kind of above objects, another kind of on the side. But these grasps, right, if we were just to sample them, aren't particularly good. We see they're penetrating the table, they're colliding with the object or inside the object at times. And so this is, kind of qualitatively showing you that this regression formulation is typically insufficient for these high degree of freedom hands. However, if we initialize with those and then optimize, we can generate grasps that are quite varied in configuration. So both overhead and side grasp here that we're showing that can grasp these objects that were not seen during training. We're getting this ability to transfer to novel objects. We can additionally explicitly model grasp type. So we can say we want a precision grasp or a power grasp, where we now have this as another contextual variable that we observe during training. And then we can either specify which kind we want, or we can have the robot infer which it would prefer to maximize success. An interesting result was that if we, let's say, just maximize success, it will always pick a power grasp because it finds those to be more probable to succeed, right? Something that we would predict from kind of prior knowledge on grasping. We've also looked at learning to reconstruct partial view objects as a signed distance field. So here again, we learn a neural network that is directly the signed distance field volumetric representation. And we can then use that signed distance field during our grasp inference procedure to ensure the hand doesn't collide with the object during pre-shape motion. And then we can also use it to guide the closing of the hand to make the fingertips in contact if we want to during the grasp control phase. And then kind of the final example I want to show of leveraging extra constraints here is we can jointly plan for the grasp and a placement location. So here we're generating both the grasp configuration, the arm configuration at time of grasping, and the arm configuration for placement. And so importantly, we see like on the left, where the object's being placed at this far corner, the robot decides to use this side grasp as it's necessary to reach this far away place. Whereas if we were to just take the most likely to succeed grasp, the robot actually wants to take a top grasp and wouldn't be able to reach it. So we need to jointly reason about these two. This can further be extended in cases where we're picking or placing into clutter. We're also reasoning about the collision geometry of the hand, not only in its configuration when it's holding the object, but when it opens it. So if we look at the video here, we'll see that the robot reaches down in a way where its fingers aren't going to collide with the objects around the object it's picking. It's then going to move it to place it on the other side of the table. And it's oriented in such a way that after it places the object and opens its fingers, it's going to, not run into this picture that's right next to it. And so, kind of to conclude this kind of first representation learning part for these affordance-based skills, right? The kind of highlights of what I want to show is that we can do large-scale simulation to enable high-quality grasping. That this inference-based planning allows us to combine our learned knowledge with kind of model-based knowledge that we already have, not requiring us not to have to leverage things like reinforcement learning to learn everything in a single policy. By using classification, we can capture multimodality over grasp. But I do want to be upfront that this inference can be expensive and slow, especially for constrained environments. This joint pick and place was particularly slow. I think there's ways we can speed it up, but fundamentally it's going to be slower than alternative representations for policies. Okay. Another thing I want to say is that here, the way we're placing objects is a purely geometric thing. We're given a pose of where do you want the object to be, and the robot tries to plan to that. And this last one is one of the big kind of limitations that we're going to start addressing in the next set of work. So we're going to kind of keep this same sim-to-real paradigm of learning with skills and having an inference-based procedure for planning, but start to reason about, for one thing, semantic goals. And at the same time, we want to extend this from single object reasoning to multi-object reasoning in our predictions. So multi-object interaction is ubiquitous in the world. We see organizations of objects all the time on bookshelves, in our homes, in kitchens, but also in industrial applications where bin picking and sorting of objects is going on, and for example, in like warehouse fulfillment, logistics operations. So we'd like our robots to also be able to reason about their effects on multiple objects at once. And so kind of motivated by the previous viewpoint, we're going to formulate a problem where we're given some set of parameterized skills now. So we might have a push, a pick, a place, etc. But now we also want to have, we're going to describe the world not just by geometry, but by some set of logical relations. So we want to be able to say things like the object 1 is to the left of object 2, or the object 3 is on top of object 2, right? Then one object is inside another container, right? Spatial relations that describe kind of semantic inter-object properties. We're going to assume that we have a segmented point cloud of some variable number of objects. So this is a really important kind of distinction, is that we're not going to be reasoning about one object or only reasoning about maximum of 2 or 4 objects, but we really want to have a representation that can scale to a variable number of objects at the time of inference. And then given some desired goal set of relations, as a conjunction of this relations in our vocabulary, we want to find a skill plan. It's a sequence of kind of which discrete skills we're going to be using, along with continuous parameters for those skills that will achieve the goal once executed. So I'm going to give a little bit of previous work in this area. So we had some previous work on reasoning about multiple objects in the context of model-free reinforcement learning. The important thing is here we're leveraging a graph neural network inductive bias to allow the robot to reason about a variable number of objects. So this was kind of the first work we had done that enabled this ability to have, many different cubes in this case on the table, but have a single policy that could operate on all of those. Okay. There's been other work in there's been a lot of work in rearrangement planning over the years in robotics, kind of more recently in terms of rearrangement for manipulation with kind of learning-based representations. A lot of work, focused on moving single objects at a time, and often would encode goals as something like a target image. Whereas I think this is something I'm fundamentally against, target images. I think if you can create an image of the goal, then isn't it already been, oftentimes you've already succeeded at making your arrangement. So I'd much rather have this logical representation, which is much more sensible to quickly define goals that the robot hasn't actually achieved. In terms of logical relations with these learning-based goals, this is also prior work that I was involved in. This with some colleagues at NVIDIA on learning multi-object relations, but only moving a single object at a time and not doing any sort of sequence planning. Right? So for this work, we wanted to kind of put together these different ideas. And the framework we used for that is going to build off of this idea of skill effects models, which comes from our friend Oliver Cromer and his student Jackie Liang. So here we still have this discrete set of skills that are all parameterized by some associated parameters. So for example, we might have a push skill that has an initial end effector pose and an offset end effector pose at the end of the pushing. For the parameters for pick and place, it might be the pick pose, the place pose. For something like opening a door, we might have the location of a handle and then a degree you want to open it, right? These are examples, right? Whatever, if you give me the skills and you give me some parameters that parameterize those skills, I'm happy to take them and put them in our model. Okay. So then given our robot and some goal, right? The skill sequencing model needs to find the discrete sequence of skills and the associated parameters that should lead the robot to this goal state. In order to do this, what was proposed by Jackie and Oliver was to learn what they call a skill effect model. Right? So this is some model, here primarily a neural network, that takes some representation of the state X, the discrete skill and its continuous parameters, and predicts the state that will result from executing this skill. So we're not going to be predicting dense in time throughout the execution, but really just the effects of the skill, hence the name, skill effects model. So the work that Jackie and Oliver were doing was doing these interesting multi-object rearrangement tasks where they would say, like, place these cubes on this little tray and then dump the tray into the bin. And they were also using, they looked at using graph neural networks to reason about variable number of objects. But all of their state representations are metric, so they're poses or positions of objects. And their goals are expressed as geometric goals, right? Place all the objects within this region. And so we were looking to extend this in two important ways. So first, to reason directly from observations, in our case, point clouds. And second, to have goal representations that are logical and not geometric. So it's an overview of the model that we propose. So we're going to have some encoder here that takes in the different object representations and encodes them into a latent state representation where we have a learned kind of representation for each different object. And we can treat those objects as nodes in a graph that's, in this case, fully connected. And this becomes the learned state representation that we can use for planning. Then, given this model and some action, we feed it into a dynamics component in our neural network that predicts the state at the results from taking that action. We can then chain these together to get sequences in an autoregressive kind of format in the latent space. But then also at each time we can decode, using our decoder psi here, to predict the relations between the objects. So this graph representation is a latent state representation that's purely learned. But the supervisory signal is these relations at future time steps. And for training, also the initial time step, right? And so we can get all of these, just like the grasp success, directly from the simulator, without anything extra. We have model-based classifiers that can tell us if one object's on top of another, left, right, etc. And so then we can train this whole model end to end by having the robot generate sequences of actions in the simulator, getting the relational labels, and and then training the model. So we've extended this a little bit to not only reason about objects that are movable, but also to include parts of the environment as nodes in this framework. So here, for example, we can have this lower layer or higher layer of the shelves. We have other relations, for example, so I haven't talked about, but so contact has always been one of the relations, but we can also reason about our things above or below now if we have these multiple object environmental configurations. And we also add a unary potential that just says, is the segment a movable object that I can manipulate, or is it part of the environment that I shouldn't try to manipulate? And this is like kind of the most simple of affordances, right? Is this something I should mess with or not? So, right, kind of in a little bit more detail, how we would then build these models is we have a point cloud convolution encoder for each segment that then it creates these latent segments. We've then moved to using, instead of a graph encoder, actually a transformer, which formally we can think of as a special kind of graph neural network, but we find them more efficient for training. So we take out our latent state, which again is tokenized kind of by the different objects. And then we can decode this for the current set seen to what are the relations, the probability of the different relations we see. Now, given our goal and some trained model, right, we can start planning over actions. Here, we're doing kind of a greedy tree-based approach where we're going to try to satisfy parts of the goal configuration conjunction until we get them. You can do much more sophisticated planning things, right? So given this, we can then do planning. right? And so we're doing very simple planning. Like I said, we're doing like a tree stage over the discrete sub-goals, and then just doing cross-entry method or some other sampling approach for getting the continuous parameters. So here's just a visualization of a scene in the simulator where we're showing that for the same initial scene, we can generate different plans to achieve different goals, just showing that we really are being able to plan with this framework. Right, and it can either, that it can get diverse behaviors for simple scenes like this when we give different goals. Here's an example of a couple of real-world scenarios. The first, the goal is to, have the coffee can be on the right of this red mug, and to put this soft scrub bottle in front of it. I think the way we have this written, the right is for the robot's view, but in front is for our view. I think it's fairly inconsistent in how the relations were defined. And then here's another example where we want the robot to put multiple objects in contact, and it actually does a pushing action that's moving multiple objects. And because of this graph representation and this learned dynamics, we're able to reason about kind of all of those objects moving at once, right? Which in all the previous work, is either you had poses of everything or you had only a single object moving, and really having this combination of the relational output and the multi-object dynamics is, I think, a very powerful representation for kind of learning general understanding of how objects can interact in the world. Here's an example of failing that I want to show just to show it's not perfect. So it's trying to push these objects into contact, but they're not quite in contact. Here's an example with environment relations where the robot is on the left just making these objects in contact on the top of the shelf. On the right, it's actually moving two of these objects from the upper shelf to the lower shelf. Right? We have more constrained motion planning required now, but the skills are still able to reason about the relations and have these stable placements. Let the robot finish here. You see, the skills here are quite simple. They're kind of heuristic-based grasping, using RT Connect for all the motion planning, right? You can make much more sophisticated skills, right, within the framework. But even for these not very robust skills, because you're learning around them in the simulator, and then you're learning, what is the probability of success for these different subtasks. By planning that over the skill parameters, you get the best of what the skills can do at runtime, right? So we get pretty high success. Okay. So this is a fun example that I like, where we created this extra condition called boundary. And so if you see on the top left, we say push to the boundary for these objects. And on the top right, we say make no objects in contact with the table. And, is it not replaying? So here we see it push to the boundary. And it stops at the edge on the right. However, it chooses a push that knocks all the objects off the table. And so what I think, we see something similar on the bottom, is these are for geometries of table that were not seen during training. But the robot has learned these very small differences in its action representation, right? The parameterization of how far it pushes can have drastically different outcomes in terms of what happens, right? Stopping right at the edge versus pushing the objects all off of it. So I think this highlights the ability of these kind of strong relational supervisory signals to train robots to understand how the geometry of the world affects what the semantics are, which I think is one of the key challenging problems to things like task and motion planning and sequencing of skills, right? How do these kind of simple semantics relate to the complex geometry of the world? These are some quantitative results to show that using either our GraphNet or transformer representation versus kind of a fully connected representation gives higher success rates for planning as we change the number of objects. Additionally, as we increase the number of goal relations in the terminal goal, we get much better success than the fully connected models. So here, we're looking at different losses. So if we instead train to predict poses and then use kind of the same heuristic classifiers that we have access to in the simulator and like treat the objects as the bounding boxes of them, the prediction of the relations is much worse, and in turn, the success rate of planning is much worse, right? So if we just try to predict the poses of everything and then decode to the relations, it's not nearly as robust as directly learning to predict the relations. And then the last one is something I didn't really talk about, but in doing this multi-step prediction at training time, we need to add what we call a latent space regularization to make the state that you predict through the dynamics matches the state that you would get by encoding from the point cloud. And if you don't do that, training doesn't work nearly as well. Okay. But we got a new workaround to that latent state encoding method, which I'm not going to go into details. This is a paper that just got accepted at ICRA. And it's my same student, Yishen, who is doing the previous work. I was on parental leave a year ago, taking care of my daughter. And so I sent Yishen to Stanford to work with Jeanette and her group and kind of extend this work. And so we did there was some clever changing of how we did the latent space to allow us to train on single step actions that you can read the paper for the details. But the other fun things we did is we added an LLM where we take the initial image, we use grounded dyno to get kind of object semantics and prompt an LLM so that now we can take a natural language command and translate it into the logical goal for the same planning framework. And I think this is a very nice way to go about using large language models because we're not having the large language model directly tell the robot what actions to do, but instead we're translating into a logical representation. We're taking natural language, translating it into a formal language, where we can then do formal verification of things, make sure that, it's logically sound what the goal is, right? That you're not putting, have logical inconsistencies in your goal. You could add extra safety checks there if you wanted. I think there's a lot of future work that can be done in this space of translating into formal languages and then using those as the representations for robots. So in doing this, we also extended the robot to doing mobile manipulation tasks. We're using external cameras here so that we're not really dealing with, changing viewpoints for the reasoning of the model. But we've also found, doing more kind of constrained packing tasks here, just showing that the new model is kind of more robust than the old one in terms of like packing objects. So here it knocked over these objects, same for another variant. I'm gonna skip these ones. Here's a fun one where Chris here is hard at work while the robot is cleaning up this scenario. So it needs to pull the bowl out, and it doesn't want to knock over the other thing. So to get this apple out of the bowl that Chris has requested, and then it can toss the apple to Chris. So snack always works, right? But so we see there's this complex relation of it needs to pull one object out to then pull out this container that contains the apple that is the target object before it can grasp that apple and toss it to Chris. Okay. So, right, this kind of series of work is the first to reason about how these logical relations will change among multiple objects and environments based on the robot actions directly from perception, right? Not having any sort of intermediate explicit modeling of the objects. Right, and it can also understand how change in observed environmental geometry relate to semantic relations between the objects. So this table example I'm talking about. And again here, like with the gross planning, we can achieve sim-to-real transfer without any fine-tuning in the real world. By having these skills as our representation and not trying to directly learn some sort of low-level policies, right, is what allows us this transfer to happen. I think that coupled with using point clouds as our representation, which again translate very well the geometry from simulation to the real world. So this is an error I made. This is what happens when you update slides at 5 in the morning. This is not highlighted yet. So I'm now going to talk about reasoning under occlusion and reasoning about what's unseen. So, right, we put stuff into containers all the time and then close those containers, right? You might put some objects in the very large American fridges we have, bigger than typical here, right? Or, you know, put your video game away after playing it, put it into a case, put that case into a drawer, close the drawer. But then at some later time, you might want your robot to retrieve one of these objects. And so far, everything I've said, the robot's reasoning directly from the perception of the current scene. How can we have the robot reason about these occluded objects? There's some work in reasoning with memory for multiple object manipulation or kind of object rearrangement. But typically, they're also kind of goal-based and only moving a single object at a time, right? So we were looking at how can we kind of capture all the things that we still had in our framework while extending it to deal with occlusion. And so in addition to just reasoning about the occluded objects, we want to, you know, achieve logical goals that involve those occluded objects. We want to think about how do we manage the memory representation we're using. And, you know, if we train in simulation, is it still going to transfer is the last question we have. Okay. So we're going to take pretty much the same model as before, and just a slightly different visualization of it, where we're going to encode our current segments into our latent space. And we're going to call this latent space now an object-oriented memory. Okay? Each of those objects has its own token in the latent space. We can decode our dynamics model through our relational detector. Here we have a pose decoder as well. And we can do our planning as before. Okay. But so now, the robot executes this one action, and we have new objects that we haven't seen before, and one of the objects we just saw has disappeared. So how can we reconcile this observation with the previous observation and our memory of where that occluded object might have gone? That is. So first, we're going to be using an unsupervised video object segmentation technique. So we're running this, what's being shown on the right. So while the robot's running its actions, we're tracking where all of the segments are moving. So now, given this new encoding, the first thing we know is that we have these new objects that appeared are unique from the object that disappeared, because the tracker tells us these are new tracks. If we then think about what happened previously, what our previous prediction was, our first idea of memory management we call LOOM for latent object-oriented memory. And we simply take the latent encoding that we previously predicted, and we can plug it into our current latent state. Because we know that we don't have any observation of this object. If we want to reason about it, we can just copy it over. Alternatively, we can do what we call DOOM for direct object-oriented memory, where we predict the pose of where the object moved, and then we take the point cloud that we observed the first time, and we transform that and put it through the encoder to get the object token in memory. But so in both these cases, right, we're going to be using an explicit object tracking approach to keep track of where objects have become occluded or not. And whenever objects become occluded, we're going to copy some representation of it based on our previous predictions. And then, right, if the robot makes a prediction about these objects, this token will propagate forward if it changes at all. So we can now use either one of these memory models within our planning framework to try to achieve goals where now these goals can reason over occluded objects that are in memory but not currently observable. Not sure why I wanted to show that video. Okay. So here's some training videos just to show that we're doing the same kind of things in simulation, but now objects are being pushed into occluded regions. We also have containers. So here the robot's putting this tall object into this skinny box. We also are moving boxes that have objects that have containers that have objects in them, excuse me. Occluding objects behind it. We really want to kind of ensure that we get diverse kind of representations of things that are hidden from view. So here's kind of an initial example of this in simulation, where the robot performs a number of actions. So it's not doing any sort of really goal-directed planning right now. It's just we're giving it a sequence of actions to kind of disturb the scene in certain ways. And then we're asking it to put the orange to the right of the mug. You might not have seen the mug was the first thing the robot put under the table. And even though it did a number of other actions to kind of move this bowl and these apples around, it still has the memory of where the mug is, multiple actions later. So it can reason about it. In contrast, if we train a kind of implicit memory model, so something like a transformer, that's just operating over the full sequence of observations in the history, and it has to implicitly learn to remember where these objects are, we find that these models forget after some horizon of actions. So if we look at our two variants, Doom and Loom, compared to this baseline, we see as the number of objects increase, performance decreases quite a bit for these implicit memory models of like transformers, or for what we call the number of distractor actions, right? So this is where we hide an object from the robot, or we have it hide it itself. Then we have it do a bunch of things that are unrelated to that object. Then we ask it to achieve some goal related to that object. And, right, this is the strength of having this explicit memory model. We can, it's stable over time. It's not getting corrupted because it's not just learned through backpropagation. So here's some real robot demos. So here we put the apple inside the pitcher. We then have the robot move the pitcher. We then say, put the apple in contact with the orange. It knows to drop the orange into the container so that it's in contact with the apple that's occluded. Here we're putting the Cheez-It box off the table. We then ask these objects to be at the boundary. This is just showing that it's reasoning about these novel objects and not being confused. This one, we're putting this green box in the pitcher. We then have it move the pitcher. We then ask it to put the green box in contact with the table, and it knows to dump it out of the pitcher, make it in contact with the table. So here, we're showing a few things. So we've hidden the mustard. Here we're showing that the segmentation and tracking is actually robust to multiple instances of the same object in the scene. It can keep an explicit memory of these different objects. And now it says, take the blue cup that's on the shelf and put it to the left of the mustard. So it's reasoning about that occluded mustard and picking up the correct object to do it. So we can now extend all these logical goals from observation to reason about occluded objects with this memory model. Right, still using the learned relational dynamics, the partial view point clouds, and leveraging this unsupervised video object segmentation as a way of getting tracking for novel objects. And we're still getting zero-shot sim-to-real transfer and manipulating a variable number of objects. And so I think this explicit object-oriented memory is very powerful for doing planning in these kinds of scenarios compared to just trying to implicitly learn a memory that generally isn't going to scale well to a variable number of objects that you might see at deployment. And we characterize that by performing well against this different number of distractor actions. So the final thing I want to talk about is how can we learn from failures after the robot's been deployed once we've trained one of these models. So here we see a few examples of the robot trying to do something and it messes up. So on the left, it's trying to place this object, this cup to the left of the other one, and it hits it. In the center, it knocks over this box of wipes while placing another one. And here it's really dumb. It's supposed to put this in the trash and it puts it on the completely wrong side of the table. So what we want to know is when the robot fails in the real world, how can we learn to correct for that? And so the first thing is, how do we detect that it failed? Well, we can use the current relational dynamics detector, so just running it on the current scene. And if the relations we predict there don't match the relations that we had predicted we would get after taking the action, we say it's a failure. It's not a perfect thing. That detector can be wrong, but we find it has very high success rates in our experiments, and more so than the predicted dynamics model. Okay? So assuming we can correctly detect the failure case, what we then want to do is generate a new batch of training data that have states that are approximately close to similar in terms of the relations that we saw prior to executing the action that failed, and that generate actions from those states that are going to maximize kind of the information gain we would get over learning from our current model. We're going to approximately do both of these things, and to do that, we're going to use something called sign variational gradient descent, which I'll define in a minute. But the main thing is we're going to generate a batch of these states and actions, which we then can in parallel execute in the simulator. So we're going to take a real to sim approach where we make the relations match what we observed in the real world. But we're going to approximate the objects in the scene by kind of planes and cuboids and cuboids with open tops for containers. So very low fidelity in terms of the geometry, but the relations are going to match. Then we'll in parallel generate this batch of executions. We'll then fine tune the model, and then we can redeploy on the real robot. And here it picks up these wads of paper, picks up the box, and now correctly puts the box in the trash. So it'll be a little bit of math. So in terms of the information gain, for a neural network, reasoning about all the possible data sets we might want to generate is totally intractable. So instead, we approximate it by the entropy of the epistemic uncertainty of our model. So gamma here is just our full relational model. And we're evaluating it under the relations that we observed in the failure case. But we want to maximize that entropy subject to states being close to the observed relations that we saw at failure. So we say the object pose O should generate the same relations with high probability or with some probability that we're going to sample from. We have some prior over states. We want the objects to be in locations that are reasonable in our simulator for training. And then here, instead of trying to reason about all possible object geometries to evaluate these samples, the C of S here is really just saying we're going to do rigid body transformations of the observed point cloud segments So we're moving around the point clouds. The robot sought failure time to generate similar relations. Then given those states, we will find the actions that will maximize the entropy over this term. Then once we've kind of decided on both these sets, we do our real to sim, we generate it in the simulator. Right? And so it becomes very efficient to do all of this just with the current model instead of having to iterate, generating simulations, evaluating under the model to get kind of fast generation. Okay. And then to sort of get these sets, I said we're going to use something called Stein variational gradient descent. I know some of you are familiar with this. We've talked about it today even. But so, right, if you're not familiar, right, in a variational inference problem, we have some intractable distribution P that we'd like to approximate with some tractable distribution Q. In the case of Stein variational inference, Q is simply a set of particles. So this would be just a set of states that we care about or the set of actions that we care about. And then we're going to optimize for those Qs to match the distribution P in terms of the KL divergence. We can do this through a gradient-based optimization. So for each particle I at iteration L+1, we take its previous location and we do a step with some step size epsilon based on this phi star gradient operator. What that looks like is the following. So we have n particles, and for each particle, its gradient step is going to be the sum of these, the log of the probability, the gradient of the log of the probability, where it is weighted by this kernel, right? And so the kernel measures the similarity between our two particles. So particles that are close are going to share the gradient. Particles that are far away will generally ignore the gradients of other particles. But then there's this second term, which is the gradient of the kernel itself. And so we can interpret these as, right, this is the similarity weighted average of gradients. So particles should follow the gradient of nearby particles. But this is a repulsive term that says, if I'm close to another particle, I shouldn't collapse to where it is, so to ensure that we get coverage over the distribution. Here's a video showing this running actually very slowly for a system identification problem for like magnet manipulation with applications to removing space debris that is completely different from what I'm talking about today. But here we're trying to do system identification of a sphere in terms of its radius and the conductivity of the metal that we've observed in it, that it's made up of based on observations of its motion. And you see that as these particles are moving, they're going to be moving to the areas of higher probability density while not collapsing onto one another too much. So then, right, if I go back to this objective, or this constrained objective, we're going to solve it by generating some state samples S plus using sign, so we get a distributional coverage over this constraint. Then given those, we can generate our actions. You can iterate between these two. We don't, because we were trying to be as fast as possible. Then given those samples, we can retrain the model. So here are some examples of the robot failing. So here, placing the bag in the wrong place, but then after training, it's in the correct place. Here, it needs to put these capsules in each of the mugs. And then it's supposed to put the cups on the other table. Yeah. So when it puts the mug on the other table on the left case, it's going to fail at one point. But then after training just on 20 more samples, it's able to achieve this same task. We have a similar case here, right? It doesn't clear enough space on the failure case to place these cups into the opening. But then after training on kind of this targeted data, it's able to make enough room to place the object where it's supposed to go. So quantitatively, we can compare this to a few other approaches. So gradient here means we also are doing optimization-based data generation, but we're not going to use Stein. We're going to just get 20 independent samples by getting random restarts for that optimization. We see we get much lower success rate after training in that way compared to getting this diverse set using Stein. Alternatively, we can use a sampling-based approach. Here we do slightly better than the gradient-based approach, but not as well as Stein. And additionally, it's computationally much more expensive to generate that than doing the Stein optimization. In red, we show what happens if the robot just tries to replan. And so we're showing that this is really a failure of the models the robot has and not kind of a minor mistake that can be corrected just by replanning. I think you should always be doing replanning on top of this, but it's, there's cases where it's not going to be sufficient. And here we get similar trends when running on the real robot instead of in simulation. So here's one last example of the robot, doing another kind of complicated hierarchical manipulation problem where we're reorganizing the drawers to achieve this task. And I do want to finally note that this method still does generalize to kind of objects and scenarios not seen during training. So in some of these cases, we intentionally trained on some slightly smaller data sets than we had before to ensure that we would get failures. But we still get good generalization after fine-tuning and are able to do longer horizon tasks, putting many objects into this box before moving it. All right, so to summarize, I've talked today about how we can endow robots with these affordance-based reasoning, how we can extend that reasoning to kind of multiple dynamically interacting objects, how we can extend that to reason about occluded objects and objects that have left the vision of the robot. And finally, I've shown you this new proposal for how we can learn from failures by generating targeted data in simulation to kind of fine-tune our models very quickly after deployment. Right, so at a high level, we've been looking at how we can use probabilistic inference to combine our deep learning approach with kind of optimization, first focused on graph planning, but then also extended to these longer sequence planning. By having these relational classifiers, we can enable planning to diverse goals, kind of represented through the conjunction of these different semantic states. The inductive bias of something like a graph net or a transformer is what enables us to reason about this variable number of objects with a single model. The relational dynamics, beyond just giving us diverse goals, also are a robust way for learning multi-object manipulation. We can use explicit memory models for reasoning about occlusion as opposed to implicit models. And targeted generation can enable a form of lifelong learning. So a couple of things we're really interested in kind of looking at next are reasoning about kind of more complex and constrained support relations during interaction, where kind of pulling one object out might be pulling on other objects because of frictions, or how can we contend with this, potentially with bimanual manipulation is one way we're looking at it. Also getting more explicit models of the uncertainty over object poses. So particularly if we're placing multiple objects into a container, we want to reach in and get one that's occluded. How can we maybe get more precise control in those situations? Also very interested in just scaling this stuff up. So not reasoning about a few objects on a shelf, but reasoning about the whole building. So this is a paper from Luca Carlone's group, Clio, which shows building of these really large scene graphs for building scale. So how do our memory models scale to that? Do we have to do extra hierarchical kind of reasoning about the model? And then finally, we want to integrate skill refinement. So not just treating those skills as fixed once they're given to us, but doing some sort of skill learning to improve performance jointly with this upper level model. Here I'm showing some RL we did for grasping recently, but we're also interested in doing this for deformable manipulation. We have funding to look at this for surgical automation. So how can we get these same kind of models that are interpretable and safe to have robots help assist surgeons during operations. Okay. And so with that, I'll conclude. And here's a bunch of the references from today. But you can find those and all of our other papers at our website. So, thank you.